So, hi guys. Today I'm going to talk about a tool that I wrote like a couple of months ago that basically invade pretty much everything on your network, starting from your IPS, IDS, sandboxes, endpoint solution, by using a simple trick, which is polyglot images. So basically, you'll get the point of the name of the tool. Basically, it just relies on cat all the time to evade pretty much everything. So who am I? I'm working for Mandiant for like 2 years now. I'm also French-Canadian, Quebecois, so please excuse my terrible accent. That's my parents' fault. I'm also the founder of the Ring Zero team, so some of you may know that website. It's actually just an online CDF that you can try challenges all years before the NSEC and make sure that you're ready for the competition. And I also really love to do like assembly code and bypass stuff. So basically, we're not going to drop any O-Day during this presentation, sorry about that, and it does going to contain some assembly. It's pretty light assembly, it's nothing super complex, but I hope you're going to love assembly after this presentation because assembly is life for me. So basically, this is a simple version of a company network. You're gonna have the cloud, which is a terrible place where there's so many malwares and people that are trying to send malware into your environment. And you're gonna try to avoid that by using IPS, sandboxes, and endpoint solution. So if you want to execute a malware on a computer inside of a corporate environment, you're gonna have to pass through all of these technologies. So I was thinking, what's the best way to actually go through all of these appliances without worrying about it? And I come up with a solution that is quite simple. Let me just check my slide. Yeah, so there's some evasion technique that you can use generally to bypass the sandbox itself. So your code going to be executed on sandbox, so you can perform like memory check, user check, disk size. There's so many bypass that you can use that are already well known, but it implied that the binary or the payload is actually executed on the sandbox, which at that point, it's kind of bad because you already know that something's executing in the sandbox. And I just wanted to avoid that part too. So I just wanted to come up with some things that do not even run on the sandbox. So I come up with the question, what can go through a sandbox without being executed? There's so many different formats. Like, for example, if you have Word, they may try to parse the macro and execute it. So if you use a malicious macro, you may be getting up flagged by the sandbox itself or the ICS that says this document do contain a macro, so it may be malicious. We just don't know, but there's a macro. Executable, DLL, PowerShell, of course, are well known. But there's some format like images that generally just don't care because parsing an image, it's kind of a waste of CPU cycle for the sandbox. So there's no point of checking an image, right? So I was going down that path. I was asking myself, is it possible to actually use an image to execute code on the endpoint? So this is actually the bitmap file header format. So it's quite simple. The format is just the magic byte, which is capital B, capital M. Then you're going to have like a couple of bytes that are used for the size. You're going to have something else. I just don't see it because I don't have the screen on my computer. But basically, you're gonna have the header that contains some other header object like the size of the images, the formats, some special things regarding the color in the images. And the cool thing about the RFC regarding bitmap, this says that the next 4 bytes used by the bitmap format are not reliable as a size for the images, which basically means that they're not used by bitmap parser. So that's quite interesting. Basically, we know that to have a valid bitmap header, we need the capital B, capital M, then probably whatever we want, then the rest of the mandatory header. So let's just give it a try, and I just manually edited a valid bitmap images by changing those bytes with garbages. So the first little white square is actually the first images, which is the unmodified image, and the second one is actually the modified image with the random header. And apparently both load properly, and actually PowerPoint parsed the image as expected. So it seems to be a valid bitmap image, which is good news for us. So we controlled those bytes. So what about trying to see what we can do with those bytes and make sure that they may be executed as a malicious payload? If you look at the BMP from a assembly perspective, if you convert these into the instruction used by Intel CPU, it's going to be converted to, I don't see, increment EDX and decrement EBP. So basically, from a shellcode's perspective, you're not addressing any memory location, you're not dereferencing memory. So if you execute these bytes as shellcode, everything's going to go well, your shellcode not going to crash. If you look at the second example, this one actually rely on differencing a location of memory. So for example, let's assume that these bytes will be converted to an instruction that look like that. Your shellcode going to be totally broken because you don't have any idea of what's inside of the register that it's going to be dereferred by the instruction itself. So seems like those two bytes are quite promising from a shellcode perspective. So we can probably just execute them as shellcode and everything's going to work as expected. So this is where I introduce the cat. So I basically asked Google for a cat bitmap images, and the first one that I get is actually that one. So someone photoshopped a cat. I think it was a perfect picture for bypassing AV solution. So let's actually take this legitimate image and modify part of it. So I just went to the end of the bits used for the images. Basically, bitmap is a super simple format, 1 bits per pixel. So I just changed some of them using CC, which is basically an instruction in assembly, which is an interrupt. And I just saved the image again. If you zoom into the image, you're going to see the top right corner of the image has been modified, of course, because we changed the bytes. So in this case, it just had a little gray line into the images. But don't get me wrong, if you look at the image full size, it's not that big. But even that, I wanted to make sure that this line got removed. So I just take a look at the format of the bitmap editor and managed to actually just edit the size a little bit. And I just changed the size editor and remove a couple of, I just reduced the height by 1. So basically the first line going to be removed. And bitmap format is so simple that basically if there's more byte in the images, they're just going to discard it. So they're just going to take the rest, load the picture, and the first line is going to be removed. And you don't see it anymore. So basically we just have the same image with a little bit, with one less height, and it still works. So now, what about the payload? So we know that we have to have the BM mandatory header. Then we can have a jump to the last part of the images to actually execute a payload that we control. So this is where it comes interesting. Basically, I don't see anything. Yep. So this is the jump instruction that I use to actually jump to the end of the images. So basically, if you remember, on this slide, if you look at the bottom images, you're going to see the bunch of C that start at a location after the start of the start of the images. So you basically just calculate the length between the jump and this location into your images, and you go end up with that value. Basically, this is just the upcode representation of the jump to that location. So if you look at the images at that point, you're going to have the BM, the jump that jump at some location inside of the images, which is something that we can control. So to test that it works as expected, I just come up with this little C code. Basically, just load a file, execute the file as shellcode. So that was just the easy way for me to test it. So this is actually the image load in Immunity Debugger. And by the way, I did the shellcoding in 34 bytes just for portability reasons, since most of the Windows nowadays still support 32 bytes. So you're pretty sure that it's going to work on both type of architecture. So this is it. This is just the loading. So basically, the little C code just gonna ended up calling a register which contained the image itself. So if you look at, just put a breakpoint before the call happened, and if you look at the address in memory, you see that this is actually the image, and you can see the BM header and the jump and the rest of the image format. So at that point, this is the beginning of the images. So as you can see, we have the two first instructions that are actually the BM, which is the mandatory header for the bitmap. Then you have your jump that jumps somewhere in the code. And as you can see on the second slide, after you hit the jump, you're going to end it up in your CC instruction, which is the one that we control at the beginning. So basically, we have a fully functional bitmap header image that is also shellcode at that point. Of course, CCC doesn't do anything super useful at that that point, but at least you know that you control a part and you can have whatever you want there. So that's the part when you actually use like a well-known shellcode like MetaPredator shellcode or Cobalt Strike shellcode, and you obfuscate it. So this is actually the image that is modified with the CCC. So as you can see, it loads perfectly on PowerPoints. This is a totally valid image. So if you send this image to a sandbox, they're just gonna check the file, analyze the error, and say, yeah, that's a valid bitmap. So there's no point of like analyzing that file because it's clearly not malicious, right? This is a super beautiful cat. Cannot be evil, right? So at that point, I don't see anything. Yep. So that's pretty much what I just mentioned. This is a valid image that is also a valid shellcode. So we have the concept behind the polyglot ideas. So now it's time to have a little bit of obfuscation on top of the payload that we're going to use. So it's quite simple. To make sure that we avoid the IDS, the sandbox, and the other product, this part is already done. We have the image that is actually valid, and sandbox is going to say, that's a cute image, I don't care. But now we have to take care of the endpoint problem. So if we just have like the MetaPredator shellcode embedded in the images, some of the tools may analyze the data itself over the network and just flag the MetaPredator shellcode, which is well known. So we have to come up with some things that actually take care of it. So there's multiple ways to do it. I'm trying to actually use the lazy way, which is a little snippet of code writing in pure assembly. And in a nutshell, the purpose of this shellcode is quite simple. It's just going to take the encrypted buffer. So I'll show you later, but basically I build a tool that take care of the encryption for you and generate the image and all the important things for you. But you're gonna have the encrypted version of the MetaPredator, which is actually encrypted using a 32-byte integer. So the first loop basically gonna brute force itself. So you have the shellcode payload, you're gonna have a 32-byte integer magic before your payload, which is unknown by the process. Only there's a line that performed the check on this value. So you're gonna have a register that get incremented on each round, and it's gonna check if the magic value XOR with that one actually match. If there's a match, you know that you actually found the key to unencrypt yourself. So the program just gonna randomly do this. It may take forever, depending on the computer that you use. One time it took like 20 minutes to get my call back because I was targeting a client that had like a 2003 super old server with probably half a core. I don't know, but it was super slow. It was probably AMD. So it takes 20 minutes to get my callback because of the brute forcing loop, and like, don't get me wrong, a 32-byte integer can go up to like billions of rounds. So if you have a CPU that takes forever for each round, it's gonna take a lot of times to actually get to the key. But once you get the key, the second loop actually just decrypt your payload. So basically the encrypted shellcode got decrypted, then the final stage of the shellcode is quite simple. It's just gonna jump to the final payload and you're gonna execute the final stager, which is whatever you want. Can be like a MetaPredator shellcode or a Cobalt Strike shellcode or whatever shellcode that you wrote on your own. So this is basically just the visual explanation of what I just told you. So basically, I don't see anything. So basically, let's assume that the key that was generated by the tool is 1337, and our magic number was 41, 41, 41, 41. Basically, the shellcode just gonna increment the register. So at some point, the register gonna contain the number 1337, 1337, and it's gonna perform the XOR operation with the value that is obfuscated in the final shellcode. And if the result equals something that match the shellcode actually understand that he found his own key to decrypt the rest of the payload. So at that point, the software is just going to continue and decode the rest of the original shellcode by using the same key over and over and by XORing each 32-byte integer of your final payload. So this is basically the last part of the second part of the shellcode. So basically, you have the loop that basically check the value inside of ECX, and if it matched the magic number, you know that you have your match. Then you can get out of the loop and continue. So EBX contains the key to be tested. EAX is pointing to the obfuscated data. The 32-byte value contained into EAX is pushed on the stack. So basically, this is just a trick to avoid null byte because I wanted to make sure that my shellcode is clean for other purposes because you want to avoid null byte in your shellcode as we discovered yesterday during the workshop. And all ECX byte are swapped because actually I just wanted to add a little bit of obfuscation in the process itself. Basically, the number that you're gonna get is not exactly the key because it needs to be swapped just to make sure that reverser may spend a little bit more time on this because they may think that this is the key, but actually it's gonna be swapped after it. But at the end, the key remained the same. And after that, the result is compared with the magic numbers and loop until ECX actually found a match. And at that point, you get the key and you're allowed to decrypt your malicious payload. So I guess that's probably, yeah, that's the second loop. That's basically the decryption loop. So it just doing a little loop. It's just gonna jump by 4 all the time because since it's a 32-byte integer, you're not working on 1 byte at a time. You're basically working on 32 bytes at a time. So basically, the loops go 4 by 4 to decrypt the block of encrypted data. And the last step is to jump to the final payload after that. So this is basically the UI for the tool. It's not the best UI ever. So you still have the sleepy cat, which void AV because he's sleepy. And you have like 5 functionality. Actually, there's only 4 in the screenshot, but there's another one that just had for conveniency. But you can host your image using a simple web server embedded into the tool. So basically, you can just run the web server that's going to deliver your images. Of course, you can host your image someone else on the internet. It's really up to you. You can also generate the image itself. So basically, you're just going to specify the shellcode that you want to execute. Then it's going to generate all the images. It's going to patch the other, make sure that everything's fit. Going to reduce the I to make sure that your shellcode do not affect the visual of the image. Then you're also going to generate the PowerShell final stage that's going to actually execute the images because you still have to run this image on your client or endpoint. So the trick that I use is actually relying on PowerShell that actually just going to execute shellcode in memory. So from a like IR perspective, you're going to see PowerShell downloading an image. And that's pretty much it. You're going to execute the image in memory. So you can probably fetch the link and you're just going to realize that this seems to be just a normal image. So if you stop there, you may lose the fact that this is not actually just a normal image, but it actually do contain a malicious payload inside of it. And after that, you can also generate the shellcode. This one already been covered. You can exit the tool, of course. And that's pretty much it. And there's actually another functionality that you can specify raw shellcode and just going to give you the shellcode format required by the tools, which is not in the screenshot at that point. So this is it. This is the tools used to, the module used to generate the payload. So as you can see, you specify the shellcode, which is actually just the default Metasploit meter predator shellcode in this case. And it's just going to generate the image for you. So it's going to do all the magic. It's a little bit verbal, so you know what's going on. Basically, it's going to patch the bitmap header, generate the random key used for the decryption. Then it's just going to patch the image that you provide. By default, the tools come with the cat image. It's really up to you to choose whatever bitmap image you want because they're all the same. Then it's just going to generate the modified version of the image. So after that, as you can see, this is the image that we generate using the cat with the meter predator payload in it. So again, you still have the bitmap header bytes. Then you're going to have your jump, that jump to the shellcode. And here's the decryption routine. So as you can see, you're going to recognize the code that we discussed a little bit earlier. So you'll see in the middle, I think it's yellow. Yep. You'll see that, yeah, it's actually light blue, but it's going to do the compare with the magic number that has been randomly generated by the tool. And at that point, when you get the key, it's going to go back to the bottom and take care of decrypting the rest of the payload. And at that point, your image has been fully executed, and you're going to jump to the official Metasploit payload, and you're going to end up having your meter predator session without being noticing over the network because your payload was fully encrypted inside of an image, which is valid. So IDS, IPS, and sandbox generally don't care about that part. On the endpoint side, of course, it really depends on the kind of solution that you have. This one, as I told you, the default payload actually rely on PowerShell, which may be detected by some endpoint solution, but there's other solutions for that I'm not going to cover during the talk because I don't have enough time. But there's a way to actually execute PowerShell without ever invoking PowerShell. So we ended up having an image that is valid shellcode. I don't know if we should be proud or feel guilty about that. It's really a question of point of view, I guess. So last step, as I told you, it's to use PowerShell to actually execute the shellcode itself. So it's quite simple. You just use PowerShell. A lot of people already wrote this kind of script. You're just allocating memory and you're taking care of pushing your bytes in it, and you just jump to it. Pretty much the same as the C code that we used earlier to test our payload. So when you're done at that point, you're just gonna go through it, and as I told you, you're gonna virtual alloc a space of allocation in memory to copy your bytes. Then you're gonna create thread and just jump to your memory location and execute it as shellcode, which is actually in this case your images. So this is pretty much the PowerShell script that the tool is gonna generate for you. In a nutshell, it's just going to perform a download strings, which is a well-known API in PowerShell that allow you to download a string from the internet, but it's never going to write the string to disk. So the image is never going to touch the disk. It's only going to be in memory, and you can execute that part of memory using the virtual alloc, the create thread, and wait for a single object to make sure that everything has been executed as expected. So this is the end goal memory delivery mechanism used by the tools. So you can use the tools to generate all of this because nobody wants to write PowerShell. I do not like to write PowerShell, at least. So the first step is quite simple. You just specify the URL where your malicious image is actually located. So specify the URL, quite simple. Then you have the tool to generate you the one-liner PowerShell. So it's just a PowerShell one-liner with the base64 encoded PowerShell code that we see earlier, which is there. So this is just feature in PowerShell. You can just encode everything in base64. That's actually quite interesting. It saves you a lot of time. And after that, you can just host the file as we created. You just start the web server on whatever port. In this case, I used the port 8080. So at that point, the image is actually stored and ready to be delivered to your victim through the internet. So that was interesting. I was able to run shellcode at that point. So I have like Cobalt Strike Beacon payload or Meter Predator payload, but I wanted to go a little bit further with this idea. I just wanted to be able to deliver whatever executable through this method. Like for example, if you want to run Mimikatz, which is a full-blown exe file, so it takes a lot of space, and how to actually execute it like using a shellcode approach. So I just do the same process with actual DLL and exe file, and I just realized that again the only two mandatory bytes at the beginning of a exe or a DLL file is actually the MZ, which is the MZ header before the PE header. So after that you have the magic and other fields that are actually not really required to make your binary fully functional. So again the header is converted to increment EDX and pop EDX. So again, nothing's gonna break your shellcode, so you're all good for that. Then you can actually do the same idea, so jump and have like a little shellcode that actually load the exe in memory and execute it. And actually, this is how Metasploit pretty much delivered their DLL after the first stage. They're using a slightly different approach, but the idea is quite the same. And funny fact, I just discovered that after I did all of that. So I should have just read about it before and save a lot of time. So usually in exe and DLL, you're going to find a bunch of null bytes that are not used at the end of some of the section that can be used to basically provide whatever you want. So we usually call them code cave. So this is the perfect place to actually put your shellcode. So the idea behind it is you're going to patch the DLL or the exe that you want to deliver automatically using the tool. And you're going to have a little shellcode inside of the code cave that actually load the binary itself in memory, place all the section, map it in memory, and just execute the exe itself. So that was the idea behind that part. And again, we just, wrong way. Basically, what you have to do is quite simple. But I mean, quite simple. I have to read the slide because I don't remember all. But you're gonna virtual unlock all the PE header. You're gonna parse the image base and the size of image. So basically, you're gonna be able at that point to map your exe in memory. After that, you're gonna virtual unlock all the sections that are defined in the headers. Then you're going to be able to import the loaded table using GAN proc address. And at that point, you can call the entry level because everything has been loaded in memory. It's like having a exe loaded, but manually instead of using the underlying operating system. So, whoa, sorry. So once the polyglot DLL or XC file has been generated, it can be embedded inside of the image. So of course, you're gonna need a little bit bigger image because usually EXE or DLL are way bigger than a simple shellcode, but you can still hide it in your image. So at that point, you're gonna have the whole EXE embedded inside of the image. The EXE gonna have the header patch that's gonna jump to the shellcode inside of the DLL or the EXE, which actually gonna load itself in memory and execute it. Which means that you can fully embed like Mimikatz, for example, inside of the image and run it remotely in memory without touching the disk and totally bypass all the network protection mechanism because it's just an image, right? So there's nothing malicious in an image. And actually, like if you look at PowerShell nowadays, they're gonna do pretty much the same. Like they're gonna load Mimikatz from a website or using a PowerShell script. But the thing is, it's easy to get access to this value because it's actually clear at some points. Even if it's encrypted over the network using HTTPS, most of the time, like those endpoint solutions gonna have like webhook or other functionality like that have visibility on the packet that your computer receives. So they're gonna flag that actually you downloaded Mimikatz and they're just gonna block it at that point. So you just have to have this layer of authentication to make sure that it goes through the network without being detected. So that's actually the links for the tool if you want to give it a try. There's no README at the moment on purpose, but I'm going to update it in the next couple of days to actually make it more user-friendly for you guys. But that's pretty much the tools and the idea behind it. So that was it for me.